So my topic is polynomial regression, and I'll be comparing the Vandermonde versus the Legendre basis. So starting off, I'll talk about the goal. So basically, like, we are using a real world time series data, which is actually derived from the Google Trends itself. We have used the query restaurants near me in India for the past 3 months data, and it's a noisy real world temporal data. So we are using it for a regression analysis. So basically what we want to understand how the choice of the polynomial basis, here the Vandermonde as well as the Legendre basis, affects the numerical stability, and also we want to answer whether changing the polynomial basis will cause any change in the fitting model, or just the numerical behavior will differ. So these are the things we're going to answer. So for that, this is the code. So first we're just loading the libraries. After that, we are loading the dataset itself. So we are basically renaming the columns and also and stuff like that. And now these are the polynomial. Also before that, we are also rescaling, because we know that the Legendre like basis is only valid between -1 to 1. So we are going to rescale into this time scale. Now we are using the Vandermonde fit. So we are using the np.vander to just get the Vandermonde fit. Vandermonde is nothing but 1 s square s cube and so on. And we are also getting the Legendre fit. So phi is the design matrix for the Legendre polynomial basis, and x is for this. So basically this returns the matrix as well as the coefficients in this case also. So we are using the least squares to actually get the desired coefficients in the end. Now after this, basically, yeah, so as mentioned in the experiment design, we have defined the estimator of y to be y hat of t, and this is basically like some ck's as the coefficients that we were talking about multiplied by the basis. So in the Vandermonde we have 1 tt square, and Legendre we have p0 p1s. So this is the orthogonal basis, which means that the inner product of any of these two like polynomials must be 0, which is not the case with Vandermonde, which actually causes a lot of issues with the numerical stability, as we will see later on. This only holds for s minus 1 to 1. So basically we are first rescaling it to -1 to 1, then we are using basically the least squares using numpy. So basically the least squares thing that I was mentioning, so this comes from np.linear-algebra.least squares. Actually this gives the these coefficients ck's which we were mentioning. And yes, so we'll use the same data for both, comparison of both. So now we will fit the polynomial models. So basically what we get is that Vandermonde as well as the Legendre actually produce the identical fitted curves, and this should be true in the sense that the fitted curves does not depend actually on the basis itself. Only the numerical representation will differ in terms of the coefficients, but the fitted curves actually won't differ in that sense. So as you can see, we have the polynomial regression Vandermonde versus Legendre. So we have used the scaled input scale, and we have basically scaled it actually back to show the representation. But like here we did scale it initially to get the s, where s is actually this 2t minus t min upon t max minus t min minus 1, which actually the normalizes this to -1 to 1. So we have used kind of the this representation. So basically we have tried for various degrees 3, 5 and 10. So for every d we have gotten the x data and the coefficients after Vandermonde fit as well as for the Legendre fits here. And after getting those values, the y hat we have actually taken as just the x dense like x transpose a basically we have taken, so into the coefficient that we obtained. So after plotting this here, as you can see for various degrees, this is the plots we get. So these two plots are actually the same. So I also have a polynomial this fitting animation with me. So as you can see, as the degrees go on to increase, this is how it tries to model and fit to the data, and too much degree would actually cause it to overfit the data. And like if the degree is very less, then it will of course have a lot of bias and not fit the data properly. Here these two actually overlap because of the fact already mentioned that both of them are actually the same thing. They're not different, just the numerical representation will be different. Now we have the two design matrices, that is like Vandermonde basis columns as well as the Legendre basis columns. So these two design matrix columns are actually vary in the correlation between them. So basically as you can see the Vandermonde column correlation, so basically like for let's say any degree, so they are actually correlated, like 11 and 12 11 and 11 are correlated, and the off diagonal values are also correlated. For example 11 example 10 and 12 here are correlated heavily. But here, as you can see, only the like 1 and 1, 2 and 2 are heavily correlated, and the others are not very much correlated. So this is also given in the PDF which was shared by the course instructor itself, that these small values actually come because we are sampling at discrete intervals, but like these values are very less. So basically we are using the X Vandermonde. So basically this is the Vandermonde design matrix, and this is the Legendre design matrix, and we are going to get the correlation between these two. After getting the correlation, this is the plotting code. So after you plot this, you get this kind of correlation matrix or the heat map that you have. Then we have the coefficient magnitude comparison. So in the coefficient magnitude comparison, what we are trying to do is that we are comparing the magnitude of the Vandermonde coefficient, that is the coefficients after we get after fitting, and the Legendre coefficients that we have. So what we get is, this is in the log scale. Basically we have plotted in the the log scale itself. So what we get here is that the Vandermonde coefficients actually blow up, and they become very high as compared to the Legendre coefficients, which remain relatively low. So basically large coefficients actually have a lot of numerical stability, because these harm you in the longer run, and like since computers have a small precision, so these large coefficients are hard to handle. And basically we'll talk something about the conditioning. So conditioning is like we'll talk later. So that's also because of the poor condition, actually we have to have larger coefficients that they can cancel out each other to get, like, let's say to represent sharper turns, let's say, or discontinuities as mentioned in the class also. So now we will talk about the conditioning of the design matrix. So when you talk about the conditioning of the design matrix, condition number is defined as this sigma max of the like the maximum singularity upon the minimum singularity of a matrix. But like what condition number effectively tells is how much amplification to error is actually done by this matrix itself. So basically, as you can see, the conditioning of a design matrix X. So we have two design matrices. We have the Vandermonde design matrix as well as the Legendre design matrix, which is nothing but like for example, for Vandermonde is going to be 1 s1 s square and basically sq up to s to the power k, and for Legendre is going to be p0 at some time t, and then p1 at time t1 and p2 at time t2, and so on and so forth. So these are the design matrices that we have. So basically, as you can see, with increasing polynomial degrees, the conditioning number actually increases a lot, and for Vandermonde it actually explodes, whereas for Legendre it does not explode that much. So the conditioning number which actually tells us how much error it actually amplifies. So for Legendre this is actually very less as compared to what Vandermonde has, which leads to the fact that it is much more numerically stable as compared to Vandermonde. So here what we have done is we have taken the degrees 1 to like effectively 1 to 15, because like, this is not included. So we have the Vandermonde design matrix, we have the Legendre design matrix. After this we what we do is we append. So basically doing the numpy's linear algebra dot condition, which directly gives us the condition number, and we append these two in these lists, and after that we plot these lists, and after plotting we get this kind of curves between them, which tell that this condition number explodes as the degrees increase. So higher degrees, it's become very hard for the Vandermonde to have a less condition number in the log scale. And then we do the noise sensitivity. So how does this condition number actually matter, and how the noise was actually amplified, which I was telling earlier. So basically what we do is we add a very small noise to the data. After adding the noise, basically what we expect is, if we add small noise to the input, the output should also have smaller noise. But this like does not happen, in the sense that adding smaller noise to the like Vandermonde case actually changes the coefficients by a lot in the Vandermonde case as compared to the Legendre coefficients. The Legendre coefficients somehow remain more or less stable, as you can see here, like the changes are very less. So this is the effect of time, noise and coefficients. So I'll show you. So let's say these were the initial Vandermonde as well as the Legendre baseline fits, right? And we have the coefficients as well. Now after that we have some noise, which is 0.1 times random. We use the normal Gaussian random noise, and we multiply by 0.1, and we simply add it to the initial y that we have, that is the predictors that we want to predict. Now after that we again refit by recomputing the new set of coefficients AV1 and BL1, which is the the coefficients of Vandermonde and Legendre after this addition of noise. We add the y noisy, and after that we plot the absolute value of the differences of these two coefficients obtained in both the cases. And this plot is of the differences in these coefficients. As you can see, the differences in the coefficients after adding a small amount of noise is too much in the case of Vandermonde as the degree increases. So you can see like these differences are very high, reaching up to hundreds, like 10 to the power 2 second order of magnitudes, and here the differences between the coefficients is very less, which is actually the indicator of the fact that small noise does not affect the coefficients much, and this is much more numerically stable as compared to the Vandermonde case. So this is the noise sensitivity and the stability conditions. So these remain more or less stable. Vandermonde coefficients change a lot. Then concluding, basically I would like to tell that like both the bases will actually fit the polynomial model, no doubt, but the numerical stability and the noise sensitivity actually depends upon the basis choice. So here one Legendre is the orthogonal, so basically for that the phi transpose phi will almost be a diagonal matrix because of the fact that the columns of phi are linearly independent of each other, or you can say like the dot product is 0. So creating phi transpose phi is more numerically stable. It is almost diagonal matrix, and actually has better sensitivity to noise. And orthogonal bases reduce the correlation, also the correlation was also very less, and better conditioning suppresses the noise amplification. So final takeaway is orthogonal polynomials do not change what we compute, but they greatly improve how reliably we compute it. So basically the difference won't be in the exact fit, but like the numerical stability and the way we compute it will be much more easier and less what do we say, prone to changes in the input, like less sensitive to the input directly. So this was it. Thank you for patiently listening.